All right, team. So, most of you know who I am. There's probably a few of you who don't know who I am. I'm Shannon Hilchey. I'm the teacher of the structures curriculum in the undergraduate and graduate program. This is my husband Dave, world-renowned structural engineer. I'm pretty good. He's the best. I try not to let it damage my ego too much, but you know, you gotta live with the hand you've been dealt. I've been dealt a pretty good hand. So most of you have heard me talk about everything that is coming in this lecture. When Sam asked me to give this lecture, I've given it in past years, so I was very excited. But I do think it's important that you hear it from a different voice. Maybe a different voice resonates with you. Maybe you're just tired of listening to me. Regardless, Dave is going to give you this brief lecture on how to pick your structural system. So again, there's no answers. These are things to help you make your choices. These are all things that you could extrapolate from the courses that I've taught you, but sometimes it's hard to make that leap of faith. So what Dave is doing here is crystallizing a lot of the things that we just don't have time to fully lay out in the structures program, because that's mandated by the accreditation system, and we only have so much time. Basically, this is the extra lecture I would love to give you if we had time. So Dave's going to take it over now. I do apologize because we're recording this early. We're talking relatively low. The children are asleep, and they are going to be waking up while he's filming this lecture, so you may see little people running through this lecture at a certain point. Hopefully not crying.
Thanks, Shannon.
And if you leave the mouse over here, they can see it. But if you bring it over here, they can't see it. You can see it, but they can't, so you have to keep it over here.
Right. Okay. Awesome. So Shannon and I have a standing joke about presentations because we've given lots of them and attended lots of them. And the worst presentations are the ones where someone stands up and reads lists of considerations and gives you no answers to anything. And this, I'm afraid, is your list of considerations lecture. This is the one lecture that consolidates all of the building systems into one lecture, which means that we can't go into sufficient depth on anything to make it particularly interesting or meaningful. But hopefully you come away with a sense of how all the pieces fit together, because you've got lots of resources for concrete, for steel, for mass timber that you can go to, and this is the one that helps you bring them together. So your project is a center for activism. There is at this point not a very explicit program that we're aware of. So when we talk about structure, we're going to speculate a little bit on the kinds of programming you might have, because that informs the kind of spaces you might need and the kind of use and dictates the building form. So we'll do that in a second, but I first want to remind you of the structural design process that Shannon has previously laid out. The first step starts with the architect. The architect selects the system and figures out the building and the layout. Obviously, nothing in this process happens without critical feedback from the balance of the team, but this is primarily an architectural task. Stage 2, the architect and the engineer work out preliminary sizing using rules of thumb and provide feedback. So we need preliminary sizing to do things like set the floor-to-floor heights. These steps are what would generally happen at say, the site plan approval process. The engineer would get involved, but often wouldn't even do a drawing. We'd just look at the architectural drawing, say, yeah, that looks reasonable, and we'd leave a little bit more room for depth of structure in this zone. The next step, the architect and engineer would figure out and calculate all the loads. So we need to determine what the assemblies are, figure out whether there's green roof, for example, and what the program is. So here are the assembly areas, here are the office areas. Stage 4, the engineer analyzes the building. including every member of the building and the system as a whole, and does the member sizing and tests that things actually work. Step 5, the engineer with input from the architect picks the member that works for each of those conditions. Step 6, rinse and repeat. Here's why we do the rinse and repeat, because the member sizing that the engineer determines is going to feed back into the structural systems. It's going to have an effect on column layout. It's going to have an effect on floor-to-floor heights. All of these things are going to feed back into the architectural design and require modifications, which are then going to feed back to the engineer to change. So there is a cyclic process that converges to a final answer, but we don't start there. It's non-linear. So our project. So this is a Center for Activism building in New York City. There is an adaptive reuse component. In an old city like New York, there is always some existing structure on every site. There aren't greenfield sites within the city of New York. And it's intended as a net zero building. So what are the kinds of spaces that we're going to need to think about in a Center for Activism? Excuse me. We know there will be a big administrative function. So administrative functions need offices. We are going to have office space. And that's going to be one type of space within the building. We are going to have a lecture hall, almost certainly. If you're going to have a Center for Activism, you need to do community outreach and teaching, and so almost certainly there's going to be a need for a lecture hall. We're going to need an assembly space. So this may or may not be the lecture hall. So someplace to host parties and other kinds of events, fundraisers, things like this may very well be in the space. And then there's all kinds of supporting function. There's parking, there's loading, there's all these other things that have to happen within the building. So here are the things that we would have to think about. We have to think about spans. That's the number one. The reason it's at the top of the list is because it's the first one we think about. Because the span demands for residential versus office versus assembly differ. We did need to think about loads, of course, because assembly areas have different loading requirements than office areas or residential areas. We need to think about height. Height is critical, particularly in an urban setting, because often we're trying to maximize site density, and we are often within a very strict zoning envelope. So we're going to have specific height requirements for spaces. Lecture halls need tall spaces, for example, and that's going to affect our structural depth. Obviously, we need to think about economy. Economy is often, or historically, has been the number one consideration. We need to think about sustainability. This is 2021. It should be the number one consideration. We have to think about fire. I mean, our project has to be code compliant, and code has very specific fire requirements, and that has a big impact on structure. Vibration and acoustics, this goes to the performance of the building, the user experience. Program issues we've talked about, and then we have to think about the founding conditions. In an urban site, particularly an old city like New York, you are not the first person to build on that site. So we are going to be in fill conditions almost certainly. We are going to encounter existing foundations. There will be site challenges. So this is the next long list of considerations. These are the things that impact structural decisions on a building. First one is the loads. We have wind loads, we have occupancy loads, occupancy being the people. We have snow load on the roof, and we have seismic loads. In New York, wind is probably the dominant lateral load. And I'm just going to take this point a moment to point out that we don't get, if we're sandwiched in a tight urban site, we don't get to design it as though we're shielded from wind. We have to consider that one or both of the buildings adjacent are going to be demolished, and we are going to be standing there on our own. So the tight urban nature of the site will have an effect in generally reducing wind speeds, but the immediate context does not. We need to accommodate movement. We really have to think hard about movement. You know, as buildings get narrower and taller, we're tightening. We're getting tighter and tighter in our considerations, and movements become more and more important to think about. So that's movement relative to adjacent buildings, for example. We have to think about fire, of course. We need to withstand the fire, and we need to maintain our fire compartments. So we have to have a structure that will not collapse before all the people get out. We can't design a structure that won't collapse. They're all going to collapse eventually in a fire. But we need to make sure they don't collapse before everybody gets out. And a critical part of that is we need to maintain our fire compartments, prevent the fire from spreading from one part of the building to another. And the structure plays a role in that. We need to withstand the environment. Now, a building like this, probably the structure is enclosed within the building envelope, and the environmental conditions are consistent throughout the life of the building, and there is not an awful lot. Where this becomes important is where we have transitions from interior to exterior. For example, we have to think about the environmental impact of uninsulated canopies and projections and things like that. We need to provide support for lateral and gravity loads. That's normally what we think of as the number one consideration is our lateral and gravity system. Structure plays a role in supporting your cladding and wall systems. And the integration of those systems is an important consideration. We think about the location. I talked about this when I talked about wind, the difference between our rural setting, a suburban setting, and an urban setting. So urban setting means we're going to get slightly lower wind loads because the kind of the density of the features tends to damp out the wind a little bit. It does mean though that we don't get snow blowing off our roofs as much, and what the snow that falls sits. We have to think about secondary support systems for mechanical and electrical equipment. So we'll have mechanical units on the roof, for example, that we have to think about. And then lastly, or firstly, we have to think about the building foundations. So let's look at, talk about spans. So residential building, the norm is about a 6.5 meter span. It was always a 6 meter span, but developers have pushed that to improve the quality of space in residential buildings, where 6.5 meters is actually very common now, or 6.6 meters. We're not in residential space. The absolutely standard office grid is 9 meters by 9 meters. That's not to say that some don't differ. 80 Atlantic, for example, is that wonderful mass timber building that was built last year by Quadrangle. That's a 6 by 6 bay. It had to be because of the structural system that was chosen. And we've got luxury, office buildings downtown that are 9 by 12 meters, for example, to get more depth to the core without interruption for light penetration and things. So 9 by 9 is not all office buildings, but I would estimate it's got to be 80% or something in 9 by 9 bay. 9 by 9 is also very common for parking. So there's a very nice integration of office over parking that happens in a 9 by 9 bay. Theaters, lecture halls, assembly spaces, often longer spans are required. We don't want a lecture hall with a 9 meter bay. That'd be a very small lecture hall. And we don't want columns interrupting views in a lecture hall. So in those types of spaces, we need longer spans. Obviously, spaces like gymnasiums need longer spans. we need to think about loose fit, long life philosophy. So the current use might be residential, say, so you could live with a 6.5 meter span. But if you're in downtown, in downtown New York, you could look at the stock of existing buildings. Downtown Toronto is not different, like the Garment District, for example. A well-designed building with a 250-year life, which is our target, is going to go through multiple uses. It's going to change. It might be residential today. It'll be an office use tomorrow. It'll be something. So it makes sense for us to design something that is generic and flexible and adaptable. We also should think of loose fit, long life in terms of the ability to adapt to future uses. So some materials are easier to adapt than other materials, and I'll elaborate that a little bit. I do want to point out that cost is not proportional to span. So cost is not proportional to building area, for one thing, that if you change your spans, your cost changes, even though your building area doesn't change. Also, though, your quantity of material is not linear. So if you have a 10% increase in span, you might have a 20 or 40% increase in material to accommodate it, depending on what is governing the member size for that particular span. So let's look at the various building materials. If we are talking about long spans, steel is the king for long spans. Steel can also accommodate very heavy loads. So 9 meter span depth in the 450 to 600 millimeter range, 12 meter depth, no problem, 600 to 800 millimeters. Very long spans, huge girder spans, 18 meter spans. All of these things are possible with steel. We can manufacture plate girders that are meters deep. I mean, you can see them in bridges and things. So steel is the king for long span because there is almost no limit. Part of the reason is that the steel is light as a percentage of the load on the building. The steel is very light, so increasing the size of the steel doesn't actually increase the demand on the steel all that much. The demand is dominated by the other loads. It's also flexible for future use, so it's easy to change steel. You can cut out pieces and weld in new pieces in the field. You can strengthen things if you need to. When we're designing a steel building, we start with our deck and work down from there. So the decision. This is an interesting. It applies to everything, but Gary Williams once told me that he owns Timber Systems in Toronto, that the structural system with the most economical deck is the most economical structural system. It doesn't seem to make any sense, completely counterintuitive, because the deck is the least expensive part of the structural system. But it's only the least expensive on a per square foot basis or on a volume basis. It's inexpensive. But there is so much more deck than anything else that if you can choose something that will reduce the quantity of deck, even though you need more beams to do it, you're probably going to wind up being a more economical structural system. That's less true with steel, but it's not untrue with steel. So here are the deck systems, and we always start here. Very typical concrete slab on metal deck. Often 63 millimeters of concrete on 38 millimeters of metal deck gives us 100 millimeters. It's very, very economical. That will span 2 meters or maybe a little bit less. The span of the deck sets up the spacing of our joists. Those joists then will have to be supported by something. They're supported by girders. The span of the joist sets up the spacing of the girders, and then the span of the girder sets up the spacing of the column. So we start with our deck and we move down. Another system that is very economical is hollow core structural, or hollow core concrete. So hollow core concrete, 200 to 300 millimeters depth, big voids, circular voids in the middle.
Remember, your mouse needs to be over here.
Oh yeah.
I am going to point out Sam is not a fan, and I feel like many of the U of T profs that I've encountered are not a fan of hollow core.
Yeah.
I'm very much not a fan.
They're not a fan of bubble deck either.
Not a fan of bubble deck either. We're telling you this because we feel we have a responsibility to let you know what's out there. What would be the worst thing in the world is for you to go out and build these things badly. Are we saying we think concrete is good or the best? Probably not. Sometimes concrete is the best if you could ignore the environmental costs. I'm sorry, I'm jumping in here. But the worst would be for you to build these things badly, so we want you to at least know they exist, but maybe we should be trying to move away from these things.
So hollow core, 200, 300 millimeters thick, roughly 50%, or maybe not quite 50%, 30 to 50% of that is void. So a 300 millimeter thick hollow core is really 150 to 200 millimeters of concrete because so much of it is voided. So it's very effective in that respect. It'll span a long way, so 30 to 40 times its thickness. At the upper end, a 300 millimeter hollow core will span 12 meters, which saves an awful lot of extra stuff, intermediate steel, and the benefit to that. I mean, we could put the steel in and save on the hollow core. All the steel needs to be fireproof, and we're gonna talk about that. And all the steel gets in the way of distribution of mechanical systems. So there's something really positive about having the clean, clear soffit. So we can put hollow, and I'm going to elaborate on some of this stuff afterwards. So this is, this is provide the thin outline and a little more detail. So another system which has not taken off, but has tremendous potential is the SPS system. SPS stands for steel polyurethane steel. Thin steel plate, polyurethane core, thin steel plate. It's a sandwich system. The SPS spans about 3 meters, but it comes panelized with 2 beams already, so that you wind up with a beam that maybe, or a deck element that's 3 meters wide, 12 meters long. It gets dropped in very quickly, and so very, very lightweight as a structural system. Let's talk about mass timber, or wood. I guess we should really, this almost should be 2 different slides, because there's mass timber and light wood framing, and they are not the same. They're as different as concrete and steel. Light wood frame is small dimensional pieces arranged closely together with a thin deck of plywood or oriented strand board. It's suitable for single-family homes and multi-story residential up to about 6 stories with a degree of fire protection. Light wood frame is combustible and has it needs to be fire protected. It has 0 inherent fire resistance. So if it starts, it burns. That's it. And really, we consider it to give 0 time for people to evacuate the building. Mass timber, as a basis, a mass timber is characterized by large dimensional pieces glued together in solid elements with flat surfaces without a lot of protuberances. So you might have a beam, but you don't have a lot of beams close together. Mass timber has a fire rating of 45 minutes without doing anything. So right off the bat, people in a building, a mass timber building that catches fire, have 45 minutes to get out of the building before there's a risk of collapse. And then we can add fire rating simply by making things a little bit bigger. So mass timber, light wood frame, very, very different. Mass timber is inherently has an inherent level of fire safety. And I'm going to talk about that. This is the span section. I just wanted to say that mass timber and light wood are not the same thing. So wood systems, mass timber and light wood, are typically good in the 4 to 6 meter bay range. That's not to say you can't do more, but that's their sweet spot, which obviously sounds problematic from for a use that has office use in it, which requires 9 meter bays. To get up to 9 meters, we're talking about big numbers. So as I said, it can be done. Like, you can do it. It's just not the sweet spot. And even 12 meter, like, you can make very, very large mass timber glulam beams. The deck in wood systems, tongue and groove, 38 millimeters for roofs, 64 for floors. We have nail laminated deck. So that's tongue and groove. These are boards on flat. We can have nail laminated deck, boards oriented vertically nailed together. This is an adaptation or a prefabricated version of the historic mill deck, which was 2x elements all nailed together. Nail laminated decks, we just make them into panels off-site and bring them in as a panel, as opposed to laying them up in the field. Dowel laminated deck is similar, just use dowels instead of wood dowels instead of nails. CLT cross laminated deck, 2x element here, 2x, 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 all glued together in the shop and brought in the panel. Bubble lam. Bubble lam is something that our office developed. This is a composite of steel and of mass timber and concrete. The idea is it gets rid of the beams. So it's mass timber panel, roughly equal thickness of concrete on top. The concrete is voided with bubbles, like bubble deck. And the idea is that it's for an asymmetric span. In the long direction, it's composite, wood and concrete acting together. In the short direction, perpendicular to the wood fiber and perpendicular to the wood joints, the wood doesn't do anything for you. So in the short direction, you're just a thin, wide concrete beam. And by doing that, we have no drops underneath. There are no beams that drop below the wood in the bubble lam system. So the sandwich wood and concrete is thickish, but overall the system is thin because we don't have the beams. Concrete. Got to talk about concrete and the environment just for a second as we talk about this. We have a very uncomfortable relationship with concrete because concrete is the best building material, which I am going to get shot for saying. But flexible, fire safe, durable, long spans, thin floor-to-floor height, good for acoustic noise transfer, good for vibration. Like, concrete checks all of the boxes as a building material. Here's the problem with concrete. Cement production accounts for 8% of global greenhouse gas emissions. 8%, one material accounts for 8%. Because the production of cement is so energy intensive. We use an enormous amount of it. I heard a statistic that China every single year builds as much with concrete as the US has ever built. Enormous amounts of it. We have a worldwide sand shortage. There are sand cartels. There are people being killed over sand. The dredging and mining of sand is doing extraordinary environmental damage because it's being, well, I should say first, the desert sand is no good for construction. It's too smooth. The wind wears it all into round marbles that don't lock together. What we need is water sand. And water sand gets dredged. It gets taken for beaches. It gets dredged out of rivers. It gets dredged out of ocean bottoms. So there's huge habitat loss. There's silting up of waterways. Habitat loss because we're removing the bottom, but also because there's no light penetration anymore in the rivers, and because it's all silted up from the dredging activities. We're destroying riverbanks by dredging, and which destroys the development on the sides of riverbanks. So worldwide sand shortage. Then to give you a sense of how much concrete is being used every year, there's enough concrete used every year to build a wall 80 feet tall, 80 feet thick all the way around the equator every single year. So just an enormous, enormous volume. Now, part of that problem is the amount of construction that we do, and that's just fueled by the population. That can't change. But concrete is extremely material demanding and energy intensive, and so whatever we can do to minimize the amount of concrete, we need to do. So I've told you that it's the best building material. Now here are the reasons. Concrete, from a span point of view, concrete is ideal. Like 6 meter spans, featureless, flat, clean soffit. There's nothing better than that for distribution of mechanical systems and penetration of natural light and everything else. 9 meters if you introduce drop panels and capitals. And if we want to go farther than that, we can introduce post-tensioning. And easily get up to 12 meter bays. We can use bubble deck. So bubble deck is a system that incorporates plastic balls, recycled H2PE plastic balls cast into the concrete, which their whole purpose is to void out all of the concrete that is not contributing to strength. So it's for strength, from bending the top and bottom is very effective. The middle's not really doing very much. And from a shear point of view, where we need what's in the middle, we only get something like 30% utilization, meaning that we've got a lot of extra capacity in shear, typically. So we put in all these voiding balls. We just take out what we don't need. And it's recycled. We're encapsulating recycled plastic, which is also a good thing. Because it's 30% lighter weight, that means we can achieve about a 15% longer span with the same thickness. Or we can, for the same span, we can be about 15% thinner. Waffle slabs and beam slabs, very effective. We can stretch out our spans, we can minimize material. It's farm work intensive, and being farm work intensive makes it expensive. We're a labor economy, and anything that adds labor to the project drives up cost. So let's look at loads. Occupied public space, we generally have 2 load categories. We have 4.8 kPa, 100 pounds a square foot for assembly areas. Assembly area includes any space on the ground floor. But it also includes any exit corridors, stairways, anywhere that people can wind up being densely accumulated. As well as the obvious intended assembly areas. And 2.4 kPa for office spaces, reading rooms, like that's the upper floor restaurant space, as long as the area is not too large, are 2.4 kPa. Heavy loads favor weak, stocky systems. That sounds strange, right? Why would we want a weaker system for a heavier load? Well, it's not that we want a weaker system for a heavier load. It's that the longer the span, let me think how to. I can't tie this directly to that statement, but I'm just going to elaborate. The longer the span is, the more likely deflection is going to control your design rather than strength. Go even farther, its vibration is going to control your design rather than strength. And so the longer the span you wind up with, the deeper the structural system, and the deeper and lighter your structural system. With weak elements, they tend to be very stocky, so there's a lot of material packed in because they're weak, which means they are inherently better for vibration and for stiffness, because you need more material because they are weak. So this is why for If you're doing an underground vault with a 10-foot span or something, then you're going to do it in concrete. That's the natural material. Not that it has to be concrete, but it is the natural material. Very heavy loads, not a long span. If you're doing a stadium, you're going to use cables, extremely strong, but the depth is going to be large. You're going to have a depth to sag ratio of 1 to 6 or something if you're doing a stadium roof, very long spans. Concrete, just to talk about the impact of load on cost. Concrete, we generally think, and this is a crude rule of thumb, which means that it's inaccurate, but it's handy. The cost is divided roughly 33% formwork, 33% rebar, 33% concrete supply in place. If we increase the load on a slab, the only thing that increases is the quantity of rebar. The labor to form it doesn't change. The quantity of concrete doesn't change. We are increasing the rebar. So we double the load, we double the rebar. It's a 16% increase in cost, roughly, according to that. So increasing load doesn't actually change the cost all that much. With wood, the cost is dominated by the cost of the wood fiber itself. We generally think of the wood fiber being 2/3 of the cost in a wood building. So double the load, now you're doubling 2/3 of the cost. So it's a significant change in wood, but not in concrete. But the impact, though, is that we should really think about designing for flexibility. When we're designing an office space, even though we could design a floor for 2.4 kPa live load plus 1 kPa of partition loads, 3.4 kPa, what we typically do is design for 4.8 kPa inclusive of partitions, with the idea that if you have an assembly space, it's a big space, it doesn't have partitions. So we increase the load about 50%, but it means that anywhere they want, they can have an assembly space on the building. We have to think about building height. So this is a Toronto regulation, but New York is probably similar. At 18 meters to the top occupied floor, we become a high rise. When we become a high rise, that has an impact on stairs, elevators, emergency exits, its number of stairs, its exiting distance, its fire ratings. There's a whole lot of things that kick in when your top occupied floor hits 18 meters. And so that becomes a very hard limit for development for a wide range of buildings. And your which? Oh, your wind load criteria changes when you become a high rise as well. Not that the wind blows differently on a building because it's called a high rise. Like, the wind doesn't change when you go to 18.1 meters versus 18 meters, but building codes have to lump things for simplicity, and so that's one of those thresholds that becomes a critical threshold. So you can imagine that if we can only get 5 stories in versus 6 stories in that 18 meters, that really has a big impact on our development potential for the site, which drives the selection of structural systems. So this 80 Atlantic project, wonderful project, Toronto's first mass timber commercial building in 100 years, 5 stories, not 6, because of the depth of structure. Weaker systems have shallower assembly depths. I mentioned this before. So you get a weaker system, you have more stuff. When you have more stuff, it can be shallower, which is counterintuitive, but true. So when we go to a beam and deck system, our overall structural depth is deeper, even though the system is lighter. So here are some rules of thumb. Like all rules of thumb, it is inaccurate, and so do not rely on it. But it's a starting place, and it will inform your thinking. So, less than 3 stories, Steel is the least economical, non-combustible building material. Light wood frame is definitely the most economical if you are allowed to build with combustible construction. 4 stories, steel and concrete are about the same. More than 4 stories, concrete is the most economical. And greater than 4 stories, steel is the most economical. Now, I'm not talking about mass timber in here. The mass timber is so new that we don't have sound rules of thumb. So I'm going to give you, there aren't archetypal buildings that we can fall back on to say, oh yeah, that one compares to that. There's no apples and apples comparisons that we can make. The general anecdotal rule is that the cost of the structure is about 15% more for mass timber. That said, I have found studies that show it's less expensive because it's faster, and if you take into account the financing cost savings, you'll get benefits. But there are such a myriad of things that are implicated in that. And we also have examples where it's double, because if you compare a mass timber building where the mass timber is exposed, which means that it is intended to be expressed, which means it is built to an architectural standard, and you compare that to a meat and potatoes concrete office building, the mass timber building is going to be substantially more expensive. So we don't have apples and apples comparisons, but the rule of thumb is it's about 15% more expensive. Mass timber, notwithstanding all the hype and excitement there is around building tall in mass timber, you're going to be very hard pressed to build all mass timber more than about 8 stories. You run out of column capacity. For example, we wind up having to hybridize our columns, put steel cores in them and things, and so once you get to say 8 stories, you're starting to hybridize your building. So the impact on economics, long spans, obviously, cantilevers, transfers. If we cannot maintain the same floor grid all the way through the building, we're going to drive the cost up. Environmental responsibility obviously has an impact on economics, because our sustainable choice is not necessarily our economical choice. Adaptive reuse. So we want to build buildings that have the ability to be reused later. Now there's some that are convinced that the idea is to make buildings like Lego sets that you actually disassemble and can reassemble without doing anything. Not convinced that that's actually going to bear fruit. Every building program is different. The chance you're going to be able to take a beam from that building and put it in that building and reuse the old bolt holes is really unlikely. We should assume that things need to be refabricated for reuse. Sustainability. So depending on the material use, I should just say that we already, engineers are trained from the beginning to minimize material use. So that's already the objective, is to minimize material use, which is one of the number one things we can do for sustainable design. But other considerations. Steel has a high embodied energy per unit weight of the material, in fact extremely high. The thing that saves steel is that you don't need very much of it on a kilogram per square meter basis. You just don't use all that much. Concrete, very high embodied energy. We talked about the energy demand in the cement production. Wood is carbon negative. So 1 cubic meter, this is another anecdotal rule that doesn't actually bear fruit, but it's close enough. 1 cubic meter of concrete will encapsulate the carbon from 1 ton of CO2. So it winds up being, as a building material, can be carbon negative. When we started doing life cycle analysis in the 90s, the capital cost of the project, that is the embodied energy of the construction, was so small relative to the embodied energy of the building that it was over its life cycle, that it wasn't really worth considering. It was always a gesture, you know. Now we have net zero energy buildings. We know how to do that. If there is a will, it can be done. When you're building a net zero energy building, the carbon capital of the construction is 100% of the life cycle cost of carbon cost of the building, and so we have to be extremely sensitive to it. Alterations, loose fit, long life. We talked about this. Steel is easy to alter. Wood is less easy, but still is relatively. You know, the wood is available. You can strengthen it. You can add to it. Concrete is pretty tough. Like, there's a limited number of things you can do in a concrete building, and when you do alter a concrete building, you typically use steel. You're not altering a concrete building with concrete all that often. Other things that impact sustainability: thermal mass. So concrete has a high thermal mass. The fact is, so does wood. Wood has a higher thermal mass per kilogram of wood than concrete does. Now that said, we use a quarter of the weight of material in wood than we do in concrete. So the thermal mass of a concrete building is higher, but not because the material is higher, but because we use so much more mass. Steel is extremely high, but we use very low mass. Concrete is highly conductive, so that the thermal energy is easily accessible, whereas that's not the case with wood. Steel has a very high recycled content, like something like 95%. But the energy in reprocessing the steel, the recycled steel, is extremely high, and so the embodied energy of recycled steel is not that much higher or lower than the embodied energy of steel made from raw ore. Wood, obviously, or maybe not obviously, but if it's not obvious yet, wood is the best from a sustainability point of view, as long as it's coming from sustainably managed forests. And generally, I mean, there are people who say that, you know, that forests are not managed sustainably, and we need to stop cutting down forests. But in fact, Canada's forests generally are growing, and something like 96% of Canada's forests meet the Forest Stewardship Council's sustainable management criteria. You think about fire. So concrete is inherently non-combustible and fire safe. Not the same thing, because wood is combustible and fire safe, or mass timber is, but concrete is non-combustible and fire safe. Non-combustible meaning it doesn't contribute fuel. It's easy to achieve long fire ratings by changing the rebar cover. So, you know, you get nominally 45 minutes or something with 3/4 of an inch or 20 millimeters of rebar cover. If we double that, we can have to, you know, 38 millimeters or 40 millimeters of cover. We can have 2.5 hour fire rating. So we can get very fire safe structures with concrete. Steel is non-combustible, doesn't contribute to the fire, but is extremely sensitive to fire. So steel, when you heat it up, loses stiffness and strength very rapidly, and so a steel building is very vulnerable to collapse in fire unless it's fire protected. So it needs to all be encapsulated in gypsum wallboard or spray cementitious fireproofing, or at the expensive end, painted with intumescent paint. Wood is combustible, meaning it contributes fuel, but in mass timber is inherently fire safe. So it takes 45 minutes for it to sufficiently weaken the mass timber building to be a danger to its occupants from a structural point of view. And if we add wood burns at typically about 40 millimeters per hour, so if we want to give the occupants an extra hour, add 40 millimeters of wood on all surfaces, and you buy your occupants an extra hour. That's unprotected. We can also protect wood with gypsum wallboard or intumescent paint, the same way you can do it with steel. Vibrations and acoustics. Acoustics. All building materials are acoustically reflective, which means that we need to acoustically mitigate. Doesn't matter what we're building with. In a concrete building, we hang acoustic panels. In a wood building, we hang acoustic panels for exposing the structure. Steel needs to be fire protected anyway, so typically we have a ceiling, and so we can incorporate acoustic mitigation into the ceiling, acoustic reflective mitigation into the ceiling. From a sound transfer, so that's a reverb issue. That's a sound reflection phenomenon. Sound transfer between floors or through walls. The thing that we need more than anything is the mass. Which means that concrete is the best. It inherently has enough mass to all concrete systems have enough mass to control sound transfer. With wood, we need to add the mass, and there's a range of techniques for adding mass, but far and away the dominant one is you add concrete. So if we're building a mass timber building and we want to manage acoustic sound transfer, we're adding something like 100 millimeters of concrete on top of the mass timber. Steel is similar, but typically with steel we have at least 65, maybe 75 millimeters of concrete on top of our metal deck, and we have a ceiling. And so with structural steel, by the time we add up all the elements in the assembly, we are in that range of 100 millimeters effectively of concrete. Vibration, concrete is massive, and because it's weak, it's massive. Because it's massive, it's stiff. Because it's stiff, it's inherently decent for vibration. So you rarely need to do vibration mitigation in concrete. Steel and wood are similar in the sense that they're much lighter and much more sensitive to vibration. It doesn't mean that vibration is a problem. It just means vibration may control the design. So we have to size our members to control vibration. So let's think about the impact of program. Well, we've talked about the 6 versus 9 meters, 6 meter residential, 9 meter office kind of bay size, 9 meter parking bay size. We also need some long spans. We're going to need long spans for our lecture theater or a gymnasium or something like that. Typically what we try to do as step one is put the long spans on the roof, because now you're not carrying floor over a long span, you're just carrying a roof over a long span. On a roof, we don't worry about vibration, we don't worry that much about, we tolerate more sag in a roof, the loads are lighter in a roof. So we start with that question. Rarely, for the assembly spaces, always want to be on the ground floor, which means that our second floor is where we migrate between our big span and our smaller spans. What that generally means is that we need, or in a condo building, it happens at the ground floor, because we have 9 meter bays for parking and 6 meter bays for residential use, and we mitigate that at the ground floor. So we manage that change using transfer beams and transfer slabs and girders. Those are, in concrete, they can be big concrete buildings, and beams in steel. In a steel building, they're obviously just bigger steel beams. We buy a little bit of extra height. In wood, they're rarely wood. You rarely can do a transfer beam in wood, so we wind up introducing, this is where we start hybridizing our building. We introduce steel into our building to accommodate the exceptional conditions. That said, I talked about bubble lam earlier. Bubble lam is one of the things that it's intended to do is to mitigate that. So we don't need to change our system. If we migrate to a bigger span, we just change the proportion of concrete to wood. We make the overall system deeper. If we need to accommodate a transfer, maybe we wind up with a 600 millimeters of concrete on 300 millimeters of wood. And concrete is doing all the work, but we haven't changed our system. So our system is still the same, the workflow is the same. So what are some other ways? We talked about um, introducing a transfer level. That's one way of mitigating it. But if we want long spans, we can also look to opportunities in the floor-to-floor range. So to do floor-to-floor trusses. So just to put that in perspective, I should talk about the Goldring Athletic Center. Goldring Athletic Center, the field house is in the basement. So that's our long span, 54-meter clear span in the basement, which is our courts. Above that, we have the gym, we have offices. Those were tighter spans in the 6-meter range. So at Goldring, what we did is we looked for the floor that had the tightest program, which was the 4th floor. That was all offices. We said, let's put a bunch of trusses in here because we can always get a door through a truss, and make the trusses full floor-to-floor height, 3.2 meters deep. They go right from the 4th floor to the roof, and they span the 54 meters, and the floors below are actually hung from those trusses. On the sides of the building, we didn't have the clear span, so the truss went full height, so it was 12 meters. It was 4-story high or 3-story high truss on the 2 sides of the building, but interior to the building it was 1-story high. Robarts Library, which you can actually walk over and look at now. The addition behind Robarts is a project that is just completing around now. That was another one which coincidentally also had a 54-meter span. At Robarts, the span was over a loading dock. And this is the kind of condition that you guys might actually start encountering if you're building on a dense urban site in New York City. There was an existing loading dock for the library that needed to be preserved, which meant that the addition to the library had to span over it. So the solution there was 4-story deep trusses on either side, and the library floor structure spanned clear from exterior wall to exterior wall. I'm going to show you this interesting image. The project started with an idea of just a big glazed wall. I mean, you'll see that it is a big glazed wall, but it was just to be a big glazed wall. And so we looked at a Virendale truss. And you know what a Virendale truss is? It's a truss that has no diagonals. Those pesky diagonals that get in the way. And the image on the bottom was a Virendale truss. This is the image from our structural analysis software. So that is the actual proportions of all the members of our Virendale truss. So it worked, 4-story deep, Virendale truss, it worked. The image above is what it turned into. So we went through a value engineering exercise. We introduced strategic diagonal elements within that elevation in order to save steel, and you can see that it saved an awful lot of steel. So Virendale trusses are possible, but they are by no means a panacea. We've got to think about the soil conditions. So, as I mentioned before, on a dense urban site, you are not the first person to build on that site. You are probably not the second person to build on that site. In fact, in New York, as in Toronto, that might not have even been land when they started building on it. It may very well have been reclaimed land that was a filled pier or something. And so you're not going to be on sort of some nice bed of glacial till. You're going to be on some mucky, weird mix of stuff and old foundations and rubble, and that's going to have an impact. So what do we do when we hit bad soil? Well, we can build typical foundations and just make them big sometimes. Sometimes what's there has some bearing capacity, just not a lot. We can use caissons. Now, caisson that's kind of local vernacular in southern Ontario. A caisson is a drilled pier. So you auger a big hole and fill it with concrete, and you make a pier that's 750 millimeters in diameter or bigger, and that's what we call a caisson that other people would call a drilled pier. We have piles. We distinguish a pile from a drilled pier because a pile is driven. A drill. I'll show some images of this. Come to think of it, maybe I'll just show the images. So here's your caisson or your drilled pier. 3 rules of thumb: diameter more than 750 millimeters. The depth in solids, like in sound material, is at least 3 times its diameter. It's a typical rule of thumb. It's a soil replacement strategy. So you remove the soil or you replace it with concrete. And it gets its capacity from end bearing and side friction. Piles or driven piles are a soil displacement as opposed to replacement. So you don't take anything out, you just drive a pile in like you're driving a nail. And there's a range of solutions there, from timber piles through precast piles. Piles are great until you hit boulders. If you've got boulders, you can't drive a pile, and that's problematic. But otherwise, piles are very effective. I should say, when it comes to timber piles, wood is like steel. It needs oxygen for decay, or steel needs oxygen for rust. Timber needs oxygen for decay. If you're in an environment with no oxygen, you're not going to get decay. So Queens Quay Terminal Warehouse in the waterfront in Toronto is on timber piles. That building was 100 years old when they turned it into condos and added a bunch of stories. It's fine on timber piles, and it'll be fine for the lifetime of the building. This pile is not going to determine the life of the building. We typically, I've had trouble finding fixed data on this, but generally below the frost level, there's no oxygen, so not that it's sewer related, but it's about that, about a meter and a half below the ground surface. You run out of oxygen, and so, like steel, if you have steel at grade, it's going to rust in a ring right at grade at the transition zone. That's where the rust is going to happen. If you have a light pole, where it's going to decay is right at grade. It's not going to, the buried part is going to last. And so what we do with timber piles is we take them up to about a meter below grade, and then we put a durable cap on. That would be like a pile cap. And that would be something that doesn't grow concrete. So here's pile groups with a concrete pile cap. Typically, the pile cap also is down below the frost level as well, because the frost will get under and jack it. So we go down below the frost level with our pile cap. And so the pile cap takes a very heavy load and distributes it to a number of piles that have finite capacity. Helical pier. So helical pier is another soil displacement strategy. It essentially just corkscrews down into the ground and bears load on each of the successive helices. You can have 1 or 2 or 3 helices, depending on the capacity you need. So these are a tremendous alternative for difficult, tight sites. A mat foundation. So if you've got poor soil, but not that poor, so you can bear on it, but your footings get so big they start to merge with each other, then you pour a mat foundation, just one big raft of concrete underneath the whole thing. So what do things look like from a structural framing point of view? Well, here's what we would typically, actually I should say that our design process in my office is that it's 3 steps. Notwithstanding the 6 steps Shannon said earlier, slightly different thing. Understand the precedent, refine as appropriate, innovate when necessary. First thing we do is, how has this problem been solved before? And if it's been solved a bunch of times, and most of those times is the same solution, chances are that's the best solution. The reason that every condo building in Toronto is cast in place concrete, 8-inch slab, 6.5 meter bay, is because that's actually the best solution. And from a wide range of factors, that's the best solution. So that's why they're all done that way. So we look at the precedent first. We're going to find that the precedent, there are conditions that we have that are not reflected in the precedent, and we're going to have to modify our system to suit whatever our existing conditions are. And then we're going to find that there are some conditions on our project where there is no precedent that's anything like it, and that's where we have to innovate. We have to invent a solution. So the first thing we do is we've got to go look at how things have been done before. This may very well be one of in the category number 3, that one of our driving constraints is net zero, and we need to build it in mass timber, which, by the way, Shannon has given you access to a lecture that the two of us did on mass timber last term, so you should watch it. But if that's a driving constraint, that is a new driving constraint that you will not find reflected in the precedents, and so that's where innovation may be required. The other thing you're going to find in some of the precedent material that Shannon will make available is some sizing guidelines, rules of thumb, which are going to be critically important for you. So a few images of structural framing. This, of course, is a concrete condo with a concrete podium on drilled piers. These are bell caissons, so you can see the little fattening on the bottom. They just use a particular type of auger that allows them to fatten the bottom of it and provide a bell. This is a structural steel project at Centennial Downsview. With a wood facade. That's what you're seeing in the foreground. But this is structural steel, light steel. This again is a steel building. This was actually an example. This was a concept for a project in China that Shannon and I worked on together, where we had very dense, tight spans. Residential program above and retail below, and so we had to negotiate a very big change in span at the ground level. Lovely image of the Goldring project. You can see very deep express truss in the foreground. Harder to see is the one-story deep trusses, 1B, and they kind of get lost in the density. And then here's our final Robarts project. This we didn't talk about because it's not relevant to this, but it is super fun. This is the Canada's Diversity Gardens at Assiniboine Park in Winnipeg. This is a large cable net, 50-meter span cable net, radial spiral cable net, which makes things extraordinarily complicated. But it'll be a cable net supporting ETFE pillows as the roofing system. Few lovely images from precedent projects from other architects and engineers, so I don't really know much about these, but they're nice reference projects anyway. This one I find, actually I'm just going to talk about this one just quickly. Not that you necessarily have this, but these folded plate roofs, think hard about this. When you fold, take a square plan and you put a fold in it, diagonal, you make it into a butterfly. You need support along that diagonal, and the span of that diagonal is the square span times root 2. It's more than 40% longer than the direct span. And so that becomes a very heavy element. And often when you're doing this, the need to fold it is a formal move that you can't perceive from anywhere. You don't see it from above. You don't see it from below. There's this a hanging ceiling. You don't see it in elevation, because what you see in elevation is all your eaves. You can create the same boundary condition connected with straight members and oriented like a hyperbolic paraboloid. So just change the pitch of each member as you go along in a particular beam, in a particular bay. So I'm talking about this bay, for example, right now. If you did that, you would wind up with, you could match all the same constraints as this solution without that giant beam. This is just an interesting way of thinking about structure and how the buildings are assembled. a structural steel frame, some popped out boxes. Here you can see we've got popped out, we have trusses on the side. So this is the same as our Robarts or our gold ring system, right? We have floor-to-floor trusses on the boundary, and then we have a structure that spans clear between those boundaries. This is a diagrid. It's interesting that it's called a diagrid because of the diamond shapes. Or maybe because dia is part of diagonal, I don't know. But anyway, diagrid because of the diamond shapes. It's really triangulated. You can see that, well, visually, what you think of is what's expressed is the diamond. It's really fully triangulated, and it's the triangulation that's the important part. The diamond doesn't give us anything. If it's quadrilateral, four-sided shapes, gives us nothing. It's the triangulation that's important. So you have to take your floor through. But once it's triangulated, now it can carry vertical and lateral loads without a supplemental system. Normally what we have is we have columns carrying vertical loads, and then we have to add cross bracing or walls or something to carry lateral loads. Once we're into a diagrid, the same system will do both. Okay, that's my last slide. Thank you for bearing with me through a long list of considerations. This is a recorded lecture, but I am looking forward to talking to you and answering questions after your session this morning.
Okay, that's great. All right, guys, I'm going to send this to Sam. It's also going to be posted, if you're watching this, you already know. It's going to be posted to the Structures 2 platform, like Dave mentioned, and it's in the slide. If you are not in my Structures 2 class, you can email Sam and he'll forward your email address to me, and then I can add you as an auditing student to my course, and that way you'll have access to all the Structures 2 material as well, if you want it. You don't have to. I'm sure Sam's going to give you this lecture slide and the sizing guidelines and the link to this, but if you want access to anything more, you also, once you are watching this video, you can see my YouTube channel, which has all the past lectures for this term, which I'm teaching Structures 1 and Structures 2 this term, but also lectures from last term. And in that, there was the third year elective that you might find interesting, just because it was Dave and I talking about when structure is architecture, so small scale elements that are just kind of interesting that you might find fun. Somebody said that their dad is an architect and was watching those things over the Christmas holidays. So, you don't have to, but if you're interested, that stuff is there as a platform for you. And I'll also make sure I share the link to the wood lecture, which I think Sam is also going to share with you guys. So, thanks, guys.